data. So if you just put them into one database and pull them out, they're unhappy. All right, so let's see, what did we do? We did types of data. We did all that. Okay, so I want to go on to big data. So the first thing I want to do is put this PowerPoint up here. Reference, no, new folder. Data. So you might want to log into Canvas someplace so that as I get stuff out there, you can pull it down. That. I put that PowerPoint up there. You don't have to open up, probably easy enough to read on the screen. Okay, so this is the first what I consider a real interesting topic. The rest of that was I was hoping it was a review of your Charlie classes. So you'll see all these names sort of used as synonyms. They're really not. There's a whole family of products and they have slightly different connotations or advantages. There's a book online which is pretty nice, and I stole some of their material. All right, so let's talk about what is big data. I mean, big data is a huge revolution over the last 10 years in the industry. It went from file systems to somebody invented SQL 30 years ago, and everything was in SQL. And then they invented this, and now probably there's way more data here because it's capable of holding way more data. So the idea is it's large, it's loosely structured, and it's data that wouldn't really fit in any of the previous technologies. So before Hadoop, like machine-generated data was ignored, not captured, because the volume was so high. There was no good way of doing it. There was no cost-effective way of doing it. So you can almost look at this as how much data you're likely to get. You can also look at this as time, as like 1970, 1980, 1990, and as time marches on, things are changing. Obviously, the cost to store a gigabyte of data has gone from millions of dollars to hundreds of thousands to thousands. Now, I don't know, 32 gigs is $10 or something ridiculous like that. So as the storage has gotten cheaper, it's more and more feasible to, in fact, save everything. Web logs, click logs, sensor data. And that's really what's going on. So now people have started saying, I can save everything that happens economically good. What am I going to do with it? Actually, it says 3 years ago, this is now 4 years ago, Yahoo was getting 60 petabytes. I assume it goes giga and then peta comes next. But
Tera.
What?
Gigatera.
Yeah, giga, tera, and then peta. So, and eBay was doing that much, 50 trillion transactions a day. Here's some more numbers from another place. Facebook, 100 trillion per events per day. Library of Congress. Boeing is capturing per flight 600 and whatever trillion bytes of information for every flight that takes off and lands. And that's another thing, I don't know if it shows up on the slides, that as this stuff became possible, immediately the government regulators got in and said, you have to save all that data. Every stock transaction, every single thing has to be stored about it, every bank transaction has to be stored, and who knows what else they've now required. So the challenge was just the sheer size of the data. And then the next one is the data is really not structured. And the lack of structure makes a relational database not a good choice for storing the data. And not many databases can store billions of rows of data anyhow, even if they could handle the data structure. So traditional data processing had something called a storage cluster. And then it's copied over to a compute cluster for processing, and then the results are written back to the storage cluster. So what that means, and companies like EMC, which went from like nothing to, I don't know what they were, $15–20 billion, maybe more, I don't know. They were huge, and I think they just got bought because the waves go down like this. They would sell you a box, and inside of the box, they would put a zillion drives. And then they had fancy dual controllers, 2 wires coming out. And then you'd have a collection of a cluster of processors. And these processors would be getting data from whatever, events, airplanes, users, whatever it was. They would format it, and then they would write it into here. And these things were designed with incredibly high-speed memory, so they could take big gulps of data in, and then they could wait around for the disk drives so they could insert the data. And then they would typically write the data on 2 drives, so if one failed, they could get it back. And if you try to read data, it can read it from either of the drive. And these storage clusters, when they started attaching them to big IBM systems, these were multi-million-dollar boxes. And then these clusters were like a group of big HP or IBM computers. They were multi-million dollars. But you can see there's this sort of this bottleneck of all the data being recorded in, and then selectively data being brought out to process it, to analyze the data. So you were just spending so much time through this relatively thin, and they literally invented their own technology for this, called fiber channel. They invented a whole new high-speed interconnect to try to solve the problem. And then the other thing that was going on was they started with computers, and then they come up with symmetric multiprocessing, so you had 2 processors, and then they come up with quad processors. And this is before chips. I'm talking about real computers. Some of the big IBM mainframes had like 128 processor boards in them. So they're trying to they were trying to scale by making the boxes more powerful, the disk drives faster, and putting more storage in here and making these wires faster. And it was very effective for many things. Like the airline reservation system or a Hertz rental car system. It was very effective, and it works, and it's still working. But it really couldn't deal with these huge, what I would call fixed data. This works when the person actually checks out of the store and submits a record, or when they actually book a ticket. It could handle that kind of event. So then, how do you store the data? There's several different ones. That's when I say with big data. Big data, it really does sort of mean NoSQL, meaning it's something different than SQL, but there's several flavors of it. One family is a simple key value store, which we often call a dictionary. You just store whatever the data is. Like you get a gulp of data from a device. You just take the data and you put it someplace and you give it a unique key. And the key could even be like a timestamp or something. So it's really fast. You can just write it. You're not spending any time processing. You're just writing, and then you can read it by index and get it back. And this is what Hadoop does, and we're going to go into this. Another one is column store. Each key is associated with some number of columns. Each column itself is a key value pair. So every row in the database can have a completely different column, and therefore they can't be normalized. What this says is, it's kind of like a SQL thing, but as you insert a row, you're putting in multiple key value pairs. And the next row of data could have completely different key value pairs. So you're not forcing the data all to adhere to one standard format. So the columns may be stored in sorted key order or not, and it lets you store any type of named data in each row, but the database can't do much for you the way a SQL database, for instance, can do things for you, because it can't make any assumptions about the data. It's all completely different. And then there's document stores, of which I think Mongo is a good example. It stores semi-structured data, JSON. And here, at least the data may be different, but it's all tagged data, so it is possible to at least process it, since the data structure is described with some sort of XML or JSONs. So it has more function, indexing fields, so then the code is not limited to query only using the key. You can do other kinds of processing. They allow fetching an entire page's data, so apparently Facebook and Amazon use these, and Mongo is a document store.
I thought Facebook still used some version of MySQL.
I wouldn't be, this site's a year old, I wouldn't be surprised if they're not using both.
Oh, right. Mongo and SQL.
So here's some examples. A simple key value store. Joe 5, Jane 12, Carlos 31. A column store. Joe, first name Joe, last name Smith. Then the next line is Jane, last name, height, weight. Next one, Carlos, first name, sport, surfing, age 23. So it's like, you can almost imagine you're spitting out a form to people, and they're putting in data, and they don't have to fill in all the fields. So you're recording whatever they put into the form, and every form that comes back has a different amount of information in different fields. So the data's there, but boy, it gets really tough to program it, to pull stuff out of it. And then we have the document store where it's sort of named. So you have a colors array, and then name fields, name values, and that's like Mongo.
So I guess Facebook uses both Hive and Cassandra. So Hive is like a data warehouse for Hadoop that supports SQL, and then Cassandra is like a multi-dimensional distributed key value store.
Yeah, we're going to talk about Hive, in fact, almost immediately. So Hadoop is an important NoSQL implementation, and my view of Hadoop, which is not great, I'm not an expert by a long shot. My view of Hadoop is the capability where you're getting lots of streams of data, and you want to analyze the data for information. So the marketing person comes in and they work for Target, and they say, look, I have all the sales history for all the Target stores for the last year. Tell me something. What does it tell you? Okay. So some data architect, analyst person starts saying, well, it could tell you this and it could tell you that. And then they hand it to a Hadoop programmer, whose job it is to program in the Hadoop language. There's no such thing, but whatever, to actually extract the data. So the sort of the goal with Hadoop is data mining, data analysis, really figure out something useful out of it. I mean, you know, as opposed, a counterexample would be a computer that's in the old days, every time you made a cell phone call, a complete record was stored of who you were, where'd you call, how many minutes it was, okay? And then another computer would read that data, process it, and calculate bills. Okay, so there's an example where you're pouring data in, and then you're processing it with a very specific goal to like create billing records, okay? This is different. This is more like you're trying to analyze, you know, is there global warming? Are more people living in the city than used to? Stuff like that, where you're doing kind of big what-if things. And the trick becomes, as you'll see, is how clever can you be at exploiting what the data is there and getting it out. So what do I got here? Hadoop. Hadoop is probably three things. It is an approach to analyzing the data. It is an approach to distributing the processing, and it's an approach to distributing the storage. And They all rely on each other, and it would absolutely not work if all three of them were not in place. So, this is an example. Suppose you had to store a lot of photographs. What's that?
Flickr.
What is it? Flickr, yeah.
Or,
Yeah, if you're Flickr, one of those, okay?
what's the other one?
So you start off, you say, okay, I'm gonna get rich, I'm gonna store people's photos.
Instagram is the other one.
So you buy a big computer with a big disk, and then, well, it's kind of full. So you buy more disks. Well, you can't fit any more disks in there, right? So you buy more computers full of disks. And now, the good news is, you know, this is now holding 16 times as much data as this, but they're not all in one namespace anymore. All your photos would not in one namespace. Now you have to specify which node, which disk, and then on down to which file. So the big thing about Hadoop clusters is they scale horizontally. If you need more storage, you add more computers. If you need more computing, you add more computers. So you just keep adding nodes. So you never, in fact, again, this sort of came into being with the massive price reduction in PC servers. At the same time this technology was kicking around, it became obvious that it's much cheaper to buy 100 PCs, each of them with a terabyte of data, than it is to buy a big honkin' IBM mainframe that has 100 terabytes of data. It's much, much cheaper. Now the IBM solution was logically one machine and one storage, so you'd think it'd be easier to program. But the numbers were so far in favor of buying 100 cheap servers. And you know, originally they literally would take, you'd see rooms full of these kinds of machines, hundreds of them all stacked in there, right? Now what they have is they have slots, and they just like take the motherboard out of here, and they just stick motherboards in these racks and racks and racks and racks. So this was driven by economics as much as it was technology. So as I said, 16 four-way processors is much cheaper than one 64-way processor, as long as you don't need shared memory. Now this was the thing, when you had a big IBM 64-way processor, each program could reference every location in memory. And they could directly access all the storage. So the programming model was really quite simple. You just referenced memory location. It didn't matter which processor you're on, it's all the same memory. That's not true when you have 16 processors or 1,600 of them. Hadoop can handle unstructured and semi-structured data. It doesn't enforce a schema on the data it stores. So you can put in arbitrary text and binary data, and Hadoop can digest any unstructured data easily. Well, I think digest means it can save it, and it can retrieve it using some key system. And we'll see why that's a good thing and why it's not a good thing. And then each node you add in a Hadoop cluster, as you add it, you've added another processor, or four, usually they're quads, to do more processing, but you also fill it up with storage, and you're now adding more storage. So, and you can even play games if you know the nature of your problem is like compute heavy. You might add a bunch of computers that are relatively lightly filled up with disk drives. And conversely, if you really wanted a maximum storage capacity, every time you added a processor, you would pack as much storage in there as you wanted. Hadoop is open source, which, everybody know what that means?
Is you don't have to pay anybody to use it.
It's more than that. It means you grab the sources and you can modify the sources to meet your need. And then typically the way the open source community works is you're required to make your changes public. So you get this spiral where multiple colleges, multiple businesses are constantly adding and improving, I think it hurts stability.